Alright, in this video we're going to find area of surface of revolution. It's a mouthful. So, this is the formula, I'm sure you've seen this before if you're on this video, of how to find the surface area of anything, like of revolution. Just take 2 pi, the integral from a to b of x times the square root of 1 plus f prime of x squared. Now, the way I approach these problems is I usually write out, I usually do what's under the square root here first. Actually, specifically f prime up till f prime x squared. So what I usually do is on the side, right under the problem, I'll write f of x is equal to x to the third. Alright, simple enough. So then we have f prime of x is going to be equal to 3x squared using the power rule. Then we have f prime of x squared, all squared, is going to be equal to 9x to the fourth. And there you go. You have whatever right here is under the square root. So the next thing we have to do is plug in, just plug this stuff into the equation, and we will get, let's see if I can fit this. I can probably fit it. This is going to be from 0 to 2, because these are the bounds, 0 to 2, so that goes what goes on the integral. 2 pi times, alright, now here's the tricky part. You have to put this x, actually this should actually be, this should be f of x, the function f of x, if it goes around the x-axis. So we technically just plug in x to the third times 1 plus f prime of x squared. See how we already solved it in this little side chart I did down here? I usually like to box it off just to show that you did it on the side. Then this would be 9x to the fourth. Alright, now building on our skills with u sub, we're going to make u is going to be equal to 1 plus 9x to the fourth. 9x to the fourth. Now, conveniently, du is going to be equal to, is it 36x to the third dx. But look at this. If you divide by 36, you get 1 over 36. Du is equal to x to the third dx. So that just means, see how this conveniently lines up, the x to the third and the x to the third. So we're actually going to be left with the integral from, let's see, 0 to 2. It's actually going to be 2 pi all over 36. Let me make the integral sign bigger so we can fit everything. It's actually going to be 0 to 2 of 2 pi over 36, because you just when you get rid of the dx, or when you bring in the du, you have to bring in the 36. That's a constant, so it just goes to the end under the 2 pi. And this will simplify to pi over 18, but I'll add that after I do the u sub. Alright, so this is actually going to be u to the 1/2 du. So, alright, so we're going to integrate this. Simple enough. It's just to 1/2. That's like a super easy integration. This is actually going to be pi over 18 from 0 to 2 of 2/3 u to the 3 over 2. Oh, oops, you gotta sub the 0 and the 2 in. So this is actually going to be, so when x is equal to 2, u is going to be equal to, so we plug 2, remember we plug 2 into, oh, some off screen, I don't have so much screen space, plugging the 2 into where the u is. So this is actually going to be, beforehand, 126. 126 at the bounds, and then the 0 is going to be 1. because it's 1 plus 9 next to the fourth, and you plug in the 1 and it just becomes, oh wait, no, it's plugging the 0, it becomes, the 9 cancels and it's just 1. Alright, so 1. So this is going to be equal to, looks like it's going to be equal to pi over 18 times 145 radical 145 minus 1. Yeah, it looks like the answer, because remember when you integrate, we're plugging in the 126 into where the u is. That will give us this, and then we're subtracting just the 1, because we're just plugging 1 to that. So I actually should probably put these two in separate parentheses just so you can visualize it. But this is technically the answer right here. So the area is equal to pi over 18 times 145 times radical 145 minus 1. So this is the answer for the area of this function right up here. So to recap, you just find the f of x, f prime of x squared, plug that right into the equation, then you can plug in where the f of x is, and usually, most of the time, whatever you plug in here will actually cancel when you do the u sub, so it actually usually comes out neatly most of the time. When I actually do these problems, they usually come out as this. They usually have like the radical 145 minus 1, but some other times it might simplify nicely so that there's no radical in the answer, and I'll show you that in the next example. Let me erase this. Hope I'm not going too fast. You can always go back and pause the video, or you can comment in the comment sections. Let me check. Oh, this one's actually going to be slightly harder. So we're going to do, what do I do here? F of y is equal to 1/3 y squared plus 2 all to the 3 over 2. And I'm off screen again. Gotta work on that. Alright, so we're going to first, like I did in the last one, we're going to find, this is f of y. We're going to find f prime of y. That's going to be equal to, let's see, 1, because we need to multiply that 1/2 times y squared. This is probably going to take up the entire board because it's a lot longer. 2 to the 1 minus 3 over 2 is 1/2 times 2y, because you're multiplying times the inside. It's easy chain rule stuff. So this f prime of y is actually going to be equal to, the 2's here are going to cancel. So we're actually going to be left with y radical y squared plus 2, because you have the 1/2 here that just makes it radical. I'd like to put the radicals in, it makes it a lot easier to read when you go through with this. So now we need to find f prime of y squared. It's going to equal, so we're taking this entire thing and squaring it, y squared, and remember when you take the square of a radical, of a square root, the square root disappears. So we're left with just y squared plus 2. And then you can actually distribute this across for this problem. Y to the 4th plus 2y. And that is, that's f prime of y squared. Now this one's going to be slightly more tricky when we go through with this. Because with this one, you can actually just plug in the y. I didn't put the bounds. Well, the bounds didn't matter up until now. But this is actually going to be from 2 to 5. So 2 pi from 2 to 5. Bounds don't matter until you solve this and all this stuff anyway. And I might actually erase this just so I have extra room for the rest of the problem. So we know that, f prime of y squared is going to be equal to y to the 4th plus 2y. And then solving this is all just getting the f to that is what matters. The f prime of y squared is what matters. So you can technically erase the other stuff, but because it doesn't really matter. So we're taking the integral from 2 to 5 of 2 pi times y. Now see, that's the trick here. This one, this one's around the x-axis, but we're still taking the y for this one. So we have y times, looks like it's going to be radical. Now this is the trick for this one. Y to the fourth plus 2y plus 1. See the plus 1 from the equation. But you see this is actually equal to y to the fourth plus 2y plus 1 is actually equal to y squared plus 1 squared. And that's the trick to this problem, is realizing the square here, the perfect square, is actually equal to that. So this is actually from 2 to 5 of 2 pi times y radical y squared plus 1 squared. And look at that. The square root actually cancels the squared. So we're left with, so I can fit this, 2 pi from 2 to 5 of y times y squared plus 1 dy. Yeah, I should have put dy on this too. So now we're just going to distribute the y. So we're left with 2 to 5 of 2 pi y to the third plus y. And look at that, dy, and look at that, it's an extremely easy integral to solve, just using simple antiderivative rules. So this is actually equal from, you only have to do a u sub for this one, 2 to 5, 2 pi times 2 to 5. So it's going to be 1/4 y to the fourth plus 1/2 y squared. Now when you do this out, it's actually going to come out to 2 pi times 6/15 all over 4 plus 15 over 2, that's for the 5, minus 4 plus 2. And this all sum up, just to save time because this video is going to be pretty long. The actual, when you simplify all this out, it's going to be 2 pi. When you simplify this here, it's going to be 2 pi times 651 all over 4, which is actually going to simplify to 651 pi all over 2. And this is the area of surface of revolution of this equation up here. So I'll actually show you the graphs on Mathematica in a little, like right after this. It's actually pretty cool. This is the, I already checked this on Mathematica, so this is the actual answer to this. So just a quick recap, just make the little chart on the side, find, write out f of x, then f prime of x, first derivative, then find what's squared of that. So then take that, just put it in the original equation, and then depending on the actual equation, you're going to want to put in x or f of x or y or f of y. In this case, we put in y. Hopefully this is helpful and it's I'm able to explain this properly. So, but the trick to this one was finding the square here, just so that cancels. If you didn't notice that, you wouldn't be able to solve it. Or actually, you technically could. It would just take a little while longer. So here, I'm going to show you on Mathematica what these graphs actually look like. Alright, like I promised, I'm going to show you the problems we did in Mathematica. Here's the first function that we found the area of. We have here x to the third, and then this is the derivative squared, like we found in the other problem. And then you just simply plug it into the formula here and hit enter. And it's supposed to be pi over 27, not pi over 18. I messed up the integration when I was doing that, so sorry about that. But look how simple that is. Just the amount of time it took me to figure it out on paper. You just plug it into Mathematica. Then I wanted to show you it three-dimensionally as well. So we have the 3D version here. This is just a sliver from 0 to 2. If you continue on, it actually becomes a bowl shape. So that's that three-dimensionally. And then we have the second function, which we found the area of, equals this. And then we just take the derivative squared, equals that. Then we just plug it right into this formula. And just to prove that this was the correct answer, we have 651 pi over 2. And three-dimensionally, it looks like this little sliver thing. So this is the area. This is 651 pi over 2, the surface area, I mean. We found that. And if you just keep going up, it just continues to spiral upwards. I think that's pretty cool. All right, so that's it for surface area and how I proved it on Mathematica. I hope this is helpful, and thanks.